Alright, hello everyone. Welcome to our today's lesson on Introduction to Polynomials. Alright, so in the next unit, we'll be working a lot with polynomials, what they are, how to add them, subtract them, all that kind of fun stuff. Alright, and one interesting thing about math is that you can always think of math as a language as well, right? Just like grammar and vocabulary, we also have things in math that help us describe what things are and how they work. Right? And the nice thing about math is that it's universal. Like everyone in the world uses the same numbers, same math, unless you're in ancient Rome or something like that. Right? So now, a major branch of math is algebra. Right? So algebra is pretty much what we've been working with the past few units. Right? This is where we use symbols like variables like x and a and b and all that. We use those symbols to represent things that we don't know. So here's some pretty cool and hip math lingos here that we use, that we've been using for probably a few decades by now. So a variable, something that we've been working with for a while, right, is a letter with an unknown real number. Right, so those are things like the X that we use, or the A's, or the B's, the C's, the H's, right? Any letters that you can think of, those are variables. And of course, could be other symbols as well. Right? We could also think of it as Greek letters, like lambda, right? Or alpha. Those are also variables. And now a term is pretty much a product of a number and a variable, or variables. Right, so it could be things like just the number 5. Right, 5 is just a number with a variable of to the power of 0. Or it could be something like 2x. That's also a term. Or things like negative 3ab squared. Right, so those are terms. Think of it as like a clump in an expression. Next is the coefficient. That's the numerical factor. Right, that's a numerical factor of a term. Right, and this is, for example, those are things like, in the case of 5x, the number 5, that's the coefficient. So that's like the number part of the term. So, or things like 1.3. Right? The 1.3 here is coefficient, even if it's a decimal. And of course, a term with just a number is called a constant. Right? So for example, this 5 here, this term 5 is also called a constant. And of course, k to the power of 3 is also a term. And the coefficient here, right, is 1. Right? We just don't write it out because we're lazy. Right? If we don't see a number in front, if we don't see a coefficient in front of a variable, we just assume it's 1. Oh, we don't assume, we just know it's 1. Right? And sometimes you get stuff like this, c squared over 4. Right? Once again, you can assume that there's a 1 in front of c squared here. So the coefficient in this case is 1 over 4. Right, so those are some some of the main terms here. A variable, that's the letter. The coefficient, that's the number in front of the letter. And the coefficient and a variable together, that is a term. So now, there are a few different types of polynomials. A monomial is just of the type a times x to the power of n. Right, so a monomial is literally just a number, a variable, and an exponent. Whereas a polynomial is just a combination of any of the monomials. So for example, a monomial could be something like 3 over 4 times y to the power of 2. Right, we got a number here, which is the a, And we got a variable, which is the y. Does it have to be x? Just have to be variable. And we have an exponent, which is the 2 here. Right? Could be things like even -4. That's also a monomial. Right? We got our number here. We got a variable here. Right? Our variable will just be to the power of 0. Right? Anything to the power of 0 is just 1. Right? Or something simple like 2x. Right? Got a number here, variable, and a power of 1. And of course, we don't write the 1 out. So, as you can imagine, polynomials right, is pretty much any combination of them. So, take 2x again, that's still a polynomial. Right, so all monomials are polynomials, but not all polynomials are monomials. It could be things like 2m minus 1. Right, that's a monomial here, that's a monomial here. Together, that's a polynomial. Right, we get something like this as well. Right, so 3 different monomials, just like that. Right, but what's not a monomial or a polynomial right, things like 1 to the power of, or 1 over x. Right, or things like 4 times the square root of x. Or things like x to the power of 2 over 3. Right, this is the reason why they're not a polynomial, is that we always have to remember that the variables right, cannot be a fraction, cannot be a root, and cannot be negative. Right, so again, we have not really learned this yet, but if we have something over a variable, then that means the variable has a power of -1. Again, we don't have to worry about that right now, but all we need to know is that the variable can only have a numerical exponent. It has to be just a number. Right? It cannot be a square root, cannot be under a fraction. Right? So things like this, right? That's completely fine. The variable here is on top of the fraction. That's fine because that's a numerator. Right? But if it's at the bottom, then that's a no-no. Okay? Next, we have the degree. The degree of a polynomial is just the sum of the exponents of all the variables. Right? And the leading term is pretty much the term with the highest degree. We'll do some practice on calculating degrees in a bit. And the degree of a polynomial is the degree of the leading term. So all those are connected here. So that sounds like gibberish, right? Let's do some examples here. Let's say we have 5x squared minus 3x plus 4. Right? The degree of each of those terms here, right? The first one is 2, right? Because that's, again, the sum of the exponent of all the variables. So in this case, the sum of all the exponents is just 2, right? The power of 2. In this one, x is to the power of 1. Yeah, if we do not write it out, it's probably 1. And in the case of the 4 here, which again is the constant, right, you can think of it as to the power of 0. Right? Because if there's no variable here, we can assume that it has to be to the power of 0, because that would make us 1. 0. Which means that in this case, the leading term is 5x squared. Right? Because, again, the leading term is a term with the highest degree. And the highest degree here is 5x squared, where it's the degree of 2. So this means that the polynomial degree the degree of the polynomial is also 2. Right? That's the degree of the leading term. For another example, let's say like -5 plus x squared y to the power of 3. Once again, if there's no variable, there's no degree, so 0. The degree here, we sum it up, right? 2 and 3. We add it up to get 5. We just add all the exponents up. Right, so the leading term has to be the x squared and y cubed, and the polynomial degree here is also 5. Right, just like that. So here's our practice here. Ooh, my Apple Pen is running low on battery, so let's see if we can finish all that real quick. Okay, so let's try this. Number of terms is the easier part. Right, we're just counting how many clumps there are. So we got our first clump, second clump, third clump here. 3 terms. Right here, we got 5 terms right here. Right, you can tell the terms because they're separated by a plus or a minus. Right here, we just have 1 term. Also 1 term here. And then right here, we got 2 clumps, 2 terms. Okay, let's check the degree. Now the degree of the polynomial. Right, the degree of the polynomial, we have to make sure that we have to look for every single degree of the terms and determine which one's the highest one. So right here, the degree is just the exponent by itself, which is 3. The degree here is the 2 plus the 1, right? We don't have an exponent, so it has to be the 1. 2 plus 1 is also 3. And the last one's degree is also 3. So the degree, the highest degree, of course, is 3. Right, the coefficients here, in this case, we got the 7, we got -2, right? Remember to include the signs in front, and a 1. Right, no numbers, just assume it's 1. Right, the constant now, in this case, again, is the term with no variables. We do not have a term with no variables, so it's just 0. Right, think of it as all this plus 0. We're lazy to write that, so we just leave it out. The leading term is the term with the highest degree. All of them are tied, so we just take the one that's the most alphabetical. That's alphabetically first. You know what I mean. Right, and as you can notice here, we give them different names. If there's 2 terms in a polynomial, we call that a binomial. 3 terms, a trinomial. Right, if it's more than 3 terms, like 5 terms here, then we call that a polynomial. But realistically, to be completely honest, I don't think this comes up again after grade 9, so again, this is just good to know for now. Okay, next, degrees here, right? We got degree of 2 here, degree of 19, of course, degree of 2, degree of 1, degree of 0. So the degree of the whole thing is 19. The coefficients here, we got a 5, a 1, a 1, a -1, right? Remember our minus signs, and a -6. So 5, 1, 1, -1, -6. The constant, right? That's the one with no variables, -6. Leading term, highest degree, of course, y to the power of 19. Next, degree. Nice and easy. This is the only term here, which is degree of 2. Coefficients, of course, just a big number in front of this exponent. Constant, there's no term without the variable, so 0. Leading term, there's no other choice other than just this. Name, because it's just only 1, it's called a monomial. 1 term. Okay, next one, degree. Right, degree, there's no exponents, right? So the degree is 0. Coefficient is just a 5 by itself. The constant, that's the term without the variable, which is just a 5 by itself. Leading term, 5 by itself. Nice and easy. Name, just 1 term, so monomial. Okay, next, degree. Very obvious one. The exponent is 102, and the degree of this term here is 0. The degree of the polynomial is 102. The coefficients here, nothing in front, so it must be a 1, and then a 4. Constant is the 4, 1 without the variable. Leading term, of course, is the one with the huge exponent. There are two terms here, so it's called a binomial. Okay, and of course we can visualize this with algebra tiles as well. Right, a big tile, a big shaded in tile is positive, a blank tile is negative. Right, a skinny one is, or the big ones is more specifically x squared, or a variable squared. One that's rectangle long and skinny is just x by itself, no square. If it's just a small square, it's a constant tile of the one tile. So in practice, right, we got negative 4x here. Negative 4x just means 4 of the negative x tiles. So 1, 2, 3, 4. And then we got plus 3. So we got 3 of the positive 1 tiles. 1, 2, 3. Right, just like that. Oh, sorry, that's a little cut off here. Just like that. Right, and of course, taking out with the squares, we got 2 of the x squared tiles. That's not a square by a long shot. So we got 2 big guys here. Minus 3x, so 3 of the skinny long ones, that's blank because it's negative. And 2 small squares because it's plus 2. So that's another way we can visualize polynomials. Now, very last step. Why do we actually care about this? Right? I mentioned earlier that math is the language, and this is how we can use it. Alright, say we have jasmine green milk tea, that's $6, and mango green tea, that's $5.50. How can we represent the amount of money that we need to spend to buy both of those drinks? Coincidentally, those are my two favorite bubble tea flavors. Fun fact. As of recording, I might change when I get older. Who cares? Who knows? Okay, so we can use an expression to represent this idea. So we can say our goal is to find out what the cost is. So we can start with C, that's the cost. Okay, and we know that a jasmine milk tea costs $6 each. So we can represent that by saying, okay, so the amount of money we spend is just 6 times how many jasmine green milk teas we'll get. We'll represent that with J. And how much money we spend on mango green tea is just 5 times 5 times however many drinks we get, M for mango. Alright, so as you can see here, we can then use this to represent any ideas that we have in math. Right? So, very important that we label all this means. C is the cost. Right, because the question is asking us for the amount of money we need to spend. Oops, I missed that. The amount of money we need to spend. So that's our cost. Right? And next, the J here is number of jasmine milk tea, green milk tea. Right? And the M stands for number of mango green tea. And that's how I represent it. So let's say, for example, I want to buy 10 jasmine green milk teas, and 1 mango green tea. Right? So I can just plug the numbers in. It'll just be, the cost will just be 6 times the 10 plus 5.5 times the 1, as an example. Right? So that's why it's very useful, because the moment we have an equation like this down, right, we can just plug in whatever numbers we need. If I have 5 drinks, 10 drinks, right, we can just plug it in and immediately get the cost. We can work backwards too. Right, so we got this equation here. 20 plus 15h. Alright, so an electrician charges this much money for the job. What does this represent? Right, so as you can imagine, because the question is saying that he's charging this much money, we can assume that the C also stands for cost here. So how much money we have to spend? 15H, right? So now, in most jobs like this, they get paid by the hour. So we can assume that, oh, the H in the 15H is hours worked. Right, so this is saying that the cost is 20 plus 15 times how many hours they have worked. Right, and of course, what does 20 mean? Right, so most likely 20 just means the starting cost. Right, so even if the electrician only spends 20 minutes, you still have to pay him at least, or pay them at least $20 as a starting cost. Right, and then we can add however many hours they've worked. Right, again, we'll practice a bit more on understanding what an equation means and making those equations. Right, but for now, just note that the whole point of polynomials is to form a language. Right, that's the language that we use to communicate. Oh, what does this number mean? How are we manipulating those numbers? Right, so that's pretty cool stuff. I know there's a lot of definitions here, but if you're confident with filling out this table over here, right, then you pretty much understand the whole lesson. Right, so yeah, try to practice a bit understanding the vocabulary and all that, and that's all. Good luck practicing.